Okay, so in this notebook, we're going to talk about what radar is, some basic definitions, what synthetic aperture radar is, some general properties of radar images, and then in the afternoon, we're going to move on to interferometry and talk about that and correlation and things that you're going to care about throughout the course of this week as you're processing a lot of data. So it's organized into three segments. The first segment is just going to be about SAR and radar in general. That's going to be this first hour. And then in the afternoon, I'm going to cover pretty quickly just the concepts of interferometry and decorrelation. All right, so this one is not going to work very effectively without the PowerPoint mode, but I'll scroll through it anyway. So first of all, we want to try to understand what is so great about interferometry. And to me, it's kind of a magical process where we start with an observation from a satellite or an aircraft or something, and you get an image, if you look at the raw data, that looks something like this. It looks like complete random noise. And you can't believe that there's actually something in there. You come around a second time, and you get pretty much the same thing, and you still can't believe that there's something in there. But through the magic of SAR processing, focusing the data, you can take that random data, reassemble the points in a new way, and create an image that actually looks something like the Earth. You can do that for both of them, and you look at these two in amplitude, they look very similar at these two different times. Now, each of these images is complex, as we'll talk about as we go along, and if you were to look at the phase of that complex image, you would see something, again, that looks completely random, as though there's no information in that phase field. But by virtue of the interferometric principles and the coherence of speckle over time that we'll talk about as we go forward, if you actually take the difference between those phases, something magical pops out. That's why this is so quite amazing. You can take these satellite observations and look at measurements of change of the Earth's surface or topography down to very fine accuracies in an image format. And then, of course, those can be used for your scientific purpose, which is a good chunk of what you're going to be learning this week in this class, how to take these data and use them for modeling. So all of this SAR imaging and interferometry relies on the wave properties of light, in particular the amplitude and the phase of that light. And for those of you who have studied electromagnetics in the past, you probably are aware that the laws that govern electromagnetic wave propagation admit for simple solutions called plane waves, which can be represented by some amplitude and a phase factor. The phase is given by omega t. Omega is the frequency of oscillation in time, minus kr. K is the direction of propagation, and r is just the position. So this form of an expression is basically a plane wave because k dot r represents a constant phase wherever r projected into this direction is constant. So the phase on this teal surface here is a constant. And by virtue of this time and space relationship, what this equation is telling you is that the electric field vector is propagating, is oscillating in time, and it's oscillating in space. In a complex sense, e to the j, that means it's cosine of this term, plus j, complex number, times sine of that term. So the electromagnetic field vector is oscillatory in space, and it's oscillatory in time. So it's this phase that we're going to be exploiting throughout everything that we do in this description. So here is our oscillating ideal plane wave in position. It has a peak-to-peak distance, which is known as the wavelength, as we all know. And the phase is defined as basically the distance along that wave from one peak to the next. So the phase is given by 2 pi over lambda times that distance. And the wavelength is related to the speed of light and the frequency of oscillation. So this phase goes to 2 pi by the time we get a distance z, which is lambda. Phase is equal to 2 pi. So the different wavelengths that we choose affect the kind of signal that we get and the kind of information we get from our radar. And there are many common bands that are used for radar observations throughout the years. This is all historically embedded in military descriptions. But nowadays we use X-band quite commonly. We use C-band very commonly. Sentinel-1 is C-band. We're starting to use more of S-band, and L-band is also up there with the ALOS and SOUCOM systems. Sometimes P-band, and you can see the wavelengths here are at the centimeter scale. So what we're seeing with these radars, as we'll talk about later, is phenomenology related to scattering off of objects that are at the wavelength scale. That's why this is so different, so fundamentally different from what you see in other parts of the electromagnetic spectrum, either very high frequencies or very, very long wavelengths. So radar, that's just a electromagnetic wave, but what is radar? Everybody has a very common knowledge of what radar actually is. You have a transmitter and a receiver, and you transmit some form of energy. It propagates some distance. It scatters off of an object like your car that the policeman is tracking, and energy comes back towards the receiver, and the distance can be measured by the time of light travel time, and if you design your system properly, you can even say something about the nature of the object that you're scattering off of. And we're all familiar with this from sound, where we have a transmitter yelling hello at the wall. It propagates some distance at the speed of sound. It bounces off some object. It's altered in some way. It's decreasing in amplitude as it goes. It scatters off in many directions and is altered to some slightly different thing, is decreased in amplitude again, and then it's received by our ears. And if we were well calibrated, we might be able to say what we were bouncing off of if we understood the difference between hello in this case and hallo, much quieter here. So this is a very simple concept. If you were running some of the examples in this and in the companion SAR processing spreadsheet, I have defined for you a number of parameters of a spacecraft flying along a regular trajectory above a flat Earth. That would allow you to compute some quantities in this spreadsheet. In this notebook later, there are a few simple equations that I was able to put in that we can play with if we want to, or you can play with on your own. Basically, it's a 750-kilometer altitude spacecraft propagating at 7,500 meters per second, looking off at 30 degrees incidence angle. In this particular case, we have a 10-meter by 2-meter antenna, and the wavelength is 24 centimeters, which is L-band, and then a bunch of other parameters here. So those may come in handy later. And here you can see they are actively defined right here in that cell. So in terms of terminology, we have the height of the platform, HP here, it's HFC defined up above. So this is where the radar is above the curved Earth surface in this particular case. Again, in my simulation, we're assuming a flat Earth, but in reality, the Earth is a curved surface. The range from the spacecraft to some point on the surface is defined as rho, which is the range. That's the distance between these 2 points. And we call this angle theta L the look angle. That's the angle from the vertical, the nadir, to the direction that we're looking. So across this swath that we illuminate, the range will be different, and this theta L will be different. The antenna itself will have some beam width. It will see some portion of the ground, and we call that angle here the beam width, theta beam width. And that illuminates a swath on the ground, which we call S. Because of local curvature, the angle here, the local incidence angle relative to the surface normal, will be slightly different than the angle here, roughly 2 or 3 degrees, depending on how far out you're looking in range. Okay, so those are some basic definitions. So one of the magical steps is to try to build up resolution in the range direction. You saw that random image on the first slides. It didn't have resolution in either dimension. In the range dimension, we want to build up resolution too. And the simplest way to do that is to have a transmitted signal that is infinitesimally narrow in time, so that if you have 2 points on the ground, you transmit your signal, it propagates at the speed of light, bounces off of the first one, some of the energy bounces back, continues propagating, bounces off the second one, some of the energy comes back. And if these echoes, if this is just a point like a mirror, you'll get back an echo that looks something similar to what you transmitted. And the narrower that pulse is, the closer those 2 points can be together for you to be able to discriminate between the two. So resolution in that case is basically determined by the pulse length. So if possible, you can use a narrow pulse to resolve these close targets. But that's not always possible, and usually you need a certain degree of power in order to get enough reflection from the ground at 750 kilometers altitude in space. So you need a better way to get better resolution, and that's usually through transmitting some sort of an encoded waveform. And that encoded waveform then would have a bandwidth associated with it, which bandwidth defines then the resolution of the observations that you're going to make. So here's just a simple calculation that you can do yourself. I define the range here through the spacecraft altitude and the look angle, and then I calculate for that. That's going to be used later. I calculate also the resolution, delta rho, that you would get just from the pulse length that I've assumed, which is in this particular case 20 microseconds, which is pretty short. And then I also calculate what the resolution would be based on a bandwidth, which is in this particular case 20 megahertz bandwidth. And if you go to the other notebook, you'll see how we generate these bandwidths through linear FM chirp, but for this purpose, we don't need to worry about that. So if you run this cell, you'll get some numbers that are available, and then you can, I've hidden the print statements, but if you run the next cell, it will show you the result of that, and you can change these numbers. So you can see that the range resolution based on a typical pulse duration of 20 microseconds is 1,500 meters, roughly. So you're not getting very good resolution if you rely on these typical radar pulse durations in and of themselves. However, if you put onto that a waveform coding that has a 20 megahertz bandwidth, then you can get a resolution of around 7.5 meters. So this is why range coding is very important to do. And again, the other notebook goes into it in greater detail if you're interested. So that's the resolution in range. Typically, for our applications, we care about resolution on the ground. You look puzzled. Is there a question? Gareth? Yeah, you just look puzzled. You're not puzzled. Okay, okay, good. Anybody puzzled? I know I didn't talk about the range coding process. That's in the other PowerPoint package, which is more detailed, but we have limited time, so we have to keep going here. So that's the range resolution, but what we mostly care about is the ground resolution. And the ground resolution is for a given slope on the ground would be given by this formula here, which is ground resolution is the range resolution divided by sine times the local incidence angle, which is this angle here. If the slope is 0, that's just this look angle here. So that is going to change as a function of range because the look angle changes as a function of range. So you can do this calculation yourself and play with it as you like. I've defined 3 different tau p's three different slopes of the ground here: 0, flat, 10 degrees, and 20 degrees. I created a vector of angles here going from 25 to 45 degrees. And then I just applied the formula 3 times. It's not the most elegant Python code, but it works. 3 different curves, 0, 10, and 20 degrees, same formula, and this is just converting from degrees to radians. And you can see what happens there with the ground resolution as a function of the look angle from 20 to 45 degrees. You can see that in the 0 slope case, there is a variability in the ground resolution from near to far range, going from, remember it started out at around 7.5 meters, and now at 25 degrees it's around almost 18 meters there, and out at 45 it's roughly, let's say 11 or 12. So you do lose resolution. So if you're designing your system to have a particular ground resolution, you have to think about that in terms of your range resolution. But you can also see as the slope starts to approach your incidence angle, the resolution can go way, way down. So you have to also worry about the resolution with regard to your slope. And we'll talk more about that later. Okay, so that's just range and range resolution. That's pretty clear, pretty straightforward. Okay, so now let's talk about radar on a moving platform a little bit. You may know this, you may not know this, but basically if you have a small antenna at a fixed wavelength, it will radiate in a large beam. If you have a very large antenna, it will radiate in a narrow beam. And the rough approximation of that antenna beam width is given by this formula, basically the wavelength divided by the length of the aperture, the antenna that you're looking at. Everybody knows what a dB is? Yes? Okay. So that's the half power point on the antenna beam is this lambda over L, roughly speaking. So we have our radar in space with its antenna dimension. It's flying along this way, and it's pulsing a pulse every, say, 1,000th of a second. And that pulse propagates to the ground at the speed of light, goes across the swath here, and then some of the energy is echoed back towards the radar. And we do this 1,000, 1,500 times per second, collect all that energy. So within that, in that radar footprint, that will be some dimension on the ground. The resolution and range is determined by either that pulse length itself or by the range coding we put on that pulse. So that can be arbitrarily fine after we do the processing. But the resolution in the other dimension is defined by the antenna beam itself. So let's look at that. So the footprint size on the ground is basically given by the range times that beam width. So range times the 3 dB beam width in azimuth is that formula, and the range times that 3 dB beam width in range in elevation is that formula. So we have a few examples down here. And you'll note I threw in a 0.866 factor in front of this just to be a little more representative of what the actual 3 dB point is in an antenna beam. But we can run that, and we can calculate what these footprint sizes on the ground actually are. And you can see that the azimuth extent, so the beam widths, the antenna beam width for this case is 1 degree in azimuth and 6 degrees in elevation. Elevation is the cross azimuth direction. So I'm flying along like this. I'm looking out this way, and this is the elevation direction as I go out towards higher elevation. And this is the azimuth or along track dimension this way. So you can see I have 1 degree and 6 degree beam widths, which gives me at the ranges of 700,000 or 800,000 meters, gives me a antenna azimuth extent of 18 kilometers and 100 kilometers. So this is because I have an antenna that's 10 meters in length in azimuth and 2 meters in length in elevation. If the antenna dimensions were different, obviously, these numbers would come out differently. So the azimuth extent would define our resolution for that one pulse for this radar system. And most of you would much prefer to have imagery that's better resolved than an 18-kilometer pixel in one dimension and, say, 10 meters in the other dimension. So we need to do something about trying to get some notion of bandwidth associated with the long track dimension so that we have bandwidth that allows us then to create finer resolution data. And that's exploiting either the synthetic aperture process or Doppler. So many of you have experienced, again, in the sound arena, an object like a train approaching you and the sound of that going up in frequency as it approaches you and going down in frequency as it goes away from you. Same thing happens with light. If you're not familiar with that, if you have a platform flying along emitting some light and it sends signal in the forward direction, that raises in frequency some, and the energy in the other direction goes down in frequency. So you get a shift in the frequency as you go from forward to back. And since we have a beam width that is a degree or so, we get a significant Doppler spectrum across any given pulse. So since we are pulsing at 1,000 or 2,000 times per second, we're flying along and we're seeing any given spot on the ground over 1,000 times as we're flying along. That point on the ground sees all these different frequencies, and that gives us then bandwidth in that direction, which gives us the ability to create a high-resolution image in that dimension. So here's an animation that is hopefully going to illustrate that, if it plays. So here's our point on the ground. Any given pulse is not so highly resolved, but the energy going, as we're going towards it, is blue shifted, higher frequency, and then as we recede away from that pulse, from that point, it becomes red shifted, and we get significant Doppler bandwidth associated with that. So that distance then, over which we see this point on the ground in any given beam footprint, could be considered the synthetic aperture length. There's actually a factor of 2 in it. So by synthetic aperture, it means that we take all of these pulses and we create an antenna that is many kilometers in length to allow us to get resolution in that dimension. In the other notebook that we are not going to go through, this is developed fully, step by step, so we can go through that. So here's a schematic of that. We're flying along. We're pulsing every millisecond or so. So we have 1,000 of these kinds of pulses. Here's our point on the ground, and this is the antenna beam width. So as we fly along, we see that point for some duration, which we're going to call, well, that's the azimuth extent. Because we're transmitting and receiving from the same platform, there's a factor of 2 in this that means your synthetic aperture is effectively twice as long as the physical distance from this point to this point. You're getting that much more phase and frequency information. So the area on the ground that we saw before is lambda times the distance divided by the antenna length, and that synthetic aperture is twice that distance because of this two-way propagation. And that antenna synthetic aperture length increases as range increases. So if this were a greater distance, then this distance here would be greater on the ground, and this distance between these points would be greater as well. So you would think that somehow range would affect the resolution that you're going to be able to get in azimuth in this case. But that also gives you a decreased azimuth synthetic aperture angular bandwidth. So the angular beam width of this synthetic aperture is lambda divided by that synthetic aperture length. Remember, lambda over L is the beam width of an antenna. Lambda over the synthetic aperture length is the beam width of this synthetic aperture. So that's this number, and if you plug in these various numbers and calculate then what the spatial resolution for that synthetic aperture then would be, basically lambda over the synthetic aperture times the range. If you plug that all in, it comes out to basically just the antenna length divided by 2. So if you remember nothing else from this lecture, this is the fundamental thing about SAR. In the azimuth dimension for strip map SAR like this, the resolution of the observation is the antenna length divided by 2, roughly. Not exactly, roughly. Okay, so that's important if you're designing a radar and you want a particular resolution. You can play with that yourself if you want. There's a little calculation here. And it just goes through those formulas above, step by step. And you can see that by the time you get through to the bottom line, the synthetic aperture resolution is half our antenna length that we started with. And you can change any of the numbers, the range or anything, the wavelength, it will still be the same, just because everything cancels through this formula. Okay, does that kind of make sense? Yes?
So how did the same SAR change the resolution with different modes?
How does the same SAR change the resolution with different modes?
Yeah.
So there's a number of ways. In range, you can change the resolution by changing the bandwidth that you transmit. In the other dimension, you can change the resolution through other tricks. One is if you have an electronically scanned antenna. We'll talk about this in a little bit. If you have electronically scanned antenna, you can divide the synthetic aperture into little pieces, and that will lower the resolution in any one swath, but allow you to get more swaths. You can also pick a point on the ground and steer the antenna to look at that point for a longer duration than just the physical sliding footprint would allow. That's called spotlighting, and that then allows you to create a longer synthetic aperture, which gives you finer resolution. But those are the kinds of tricks in azimuth that you would do. Okay? Okay, so many of you have probably heard that these images that you get, these complex images with amplitude and phase, are delivered often in range Doppler coordinates. As a result of this discussion, I think you now understand range, if you didn't before. Range is the distance from the platform to a point on the ground, and a constant range is determined by these circles on the ground. And then the Doppler would be this 2v dot L. V is the velocity vector, L is the look vector, divided by the wavelength. And those would look like these sort of hyperbolas on the ground here. So range and Doppler, at least locally within the footprint, form a quasi-rectilinear coordinate system. And so many of the older processing techniques actually just processed through Doppler. They basically took an FFT after some phase correction, and that was it. You had a Doppler representation, and it looked like an image. And there is a one-to-one representation between the Doppler and the actual position on the ground. And you can see that if you're looking off to the side here, called broadside illumination, that you are quasi-rectilinear. This is highly exaggerated. Remember, the azimuth extent of this beam was 1 degree for our 10-meter antenna. So this is very, very narrow position on the ground. So these contours really are quite orthogonal in that very narrow beam footprint. But sometimes systems are squinted forward or back. this is our broadside case. If the antenna happens to be pointed forward, then we call it forward squint, and backward squint. I lost a symbol here, but this is the phase trajectory of a point going through that, going through the time history here. So if we're forward squinted, we're looking at one piece of a target's phase history or Doppler history. And if we're backward squinted, we're looking at a different piece. And if you looked at the spectrum of this energy in the along track dimension, if you're looking broadside, the spectrum would be centered around 0. So some of the Doppler frequencies would be negative, some would be positive. If you're forward squinted, you would have all positive, and backward all negative. So this is what the spectrum would look like. Many people prefer zero Doppler geometries because it's more like a coordinate system, and this seems to be becoming a standard for how one would deliver these data. Even if the data were acquired in a forward squinted geometry, there are ways to process it to make it look like it was acquired in this broadside case. You have to be careful about phase and all that kind of stuff, but it can be done. And that's because, well, I'll skip this one. It's hard to see this. This is trying to illustrate that if you're processed in this broadside case, as you're sliding this along, everything remains sort of rectilinear in this strip map mode. Whereas if you're squinted forward, everything is sort of skewed relative to a natural coordinate system relative to the flight direction. So this seems to be becoming a standard, and I guess all of our products in ICE are now zero Doppler, or not. They can, but they're not all zero Doppler. Yeah. So you need to know a little bit about both. All right, so as I mentioned, if you want to learn more about SAR, this is a very high-level thing, and I realize probably for some of you this is probably quite confusing. There is another notebook called the SAR Processor Tutorial. I'll go there just quickly. I think I still have half an hour. Go back to notebooks, and if you go to SAR Processor Tutorial, this also is a notebook supported by some figures in a subdirectory. This one, if you click Run All Cells, will take probably 20 minutes, so probably not the best thing to do right off the top of the bat here, and it's a little slower on this system than it is on my laptop, so it might even take longer. But what this does, here you can see, I'll just go over the outline here. And I was very proud of myself for figuring out how to link. You can click on any one of these things and it'll go down to the right spot in the notebook, so you don't have to scroll through the whole thing. Anyway, it talks about the background, the SAR geometry, antenna patterns. So if you're confused about this beam width stuff I just described, you can learn a little bit more about it here. The beam width and the swath width and their relationship to the antenna patterns. And it talks about, in detail, about the phase and Doppler frequency in the synthetic aperture and the resolution. The same description I just gave you, it goes over here in greater detail. And there's quite a bit on the radar equation, which talks about the noise quality of your data. I have one slide in this other package we'll get to shortly, but this goes through the entire derivation of the radar equation, which also is quite instructive. Yeah.
Comment on the similarity between this and sonar and also LiDAR as a part of that, and whether the equations work for both, for the different...
The equations. I think that to first order, they're the same equations. Yes. I mean, the LiDAR and the radar, definitely. It's hard to do synthetic aperture LiDAR, but I guess people do. And there's lots of complicating factors with LiDAR in terms of turbulence in the atmosphere that we tend to ignore in radar. For sonar, similarly, I mean, it's sound instead of light, so the propagation constants and everything are different. And the water also produces lots of refractive problems that we tend to ignore in SAR. But to first order, it's pretty much the same thing.
Thanks.
For sonar?
No, for LiDAR. LiDAR, they're starting to look at like full waveform LiDAR, actually.
Well, that's true, yes.
So those are different.
Yeah, you could probably do synthetic aperture full waveform LiDAR as well and do full reconstruction of the volume. Yes, anyway, going on here. So this simulation allows you to construct 3-point targets. If you want more point targets, you can change the code. I just selected 3 to keep it fast. It talks about simulating the transmitted pulse with the coded waveform, so you can play with the coding of the waveform, and then simulating the received echoes. I'll scroll down quickly to show you. Then it talks about focusing the data in range to build up the resolution. There's a sort of correlation operations that need to be done, and these can be done in the time domain or the frequency domain. This goes through both of those cases. And then focusing the data in the azimuth domain, using that bandwidth, the Doppler bandwidth, to focus it, also can be done through correlation, both in the time domain and the frequency domain. And then this other technique called back projection. So just to give you a quick example, I scroll down, that's the antenna pattern in 2 dimensions. It talks about the phase history, but I just wanted to get down to. So there's my point target, 1 corner reflector. This would be simulated echoes. This is the long track dimension. This is the range dimension. So 1 point target creates a pulse for each time step, a pulse of energy, and it's shaped by the azimuth antenna pattern. These are the nulls of the antenna pattern. So that's the simulated data. There's some noise you can add to it, and you can compress the data, get your resolution and range. Shows you some cuts through that, different techniques, and so forth. So it's quite complete. This is what a poorly focused corner reflector looks like. And down at the bottom, you get some, this tells you why it's poorly focused and how you can make it better. And then these are better focused. So if you're interested, please feel free to take time, and I can run you through it later on in the week if you're interested. Okay, so going back to this. Okay, so CSAT was the first civilian SAR in space, launched in 1978. It lasted only 3 months in orbit. Unfortunately, the power system failed, but it was enough to demonstrate almost everything that we use routinely today, especially in terms of interferometry, maybe not polarimetry. But you can see this is Death Valley, one of the first images taken from CSAT. CSAT was an L-band system, 24 centimeter wavelength, so sensitive to structures of that scale size. Okay, so we've been talking mostly about this strip SAR case, where this is a standard mode that many historical systems have used, like CSAT and RadarSat and such, where you have a antenna, you transmit a pulse every millisecond or so, and you just continuously do that and map out a strip or a swath. That gives you some ability to map the Earth, but often people would like much more area. So if you have a sophisticated enough antenna that allows you to change the pointing direction essentially instantaneously, electronically, then you can operate in scan-SAR mode, where you transmit a set of pulses for some portion of the synthetic aperture, and then you repoint the antenna electronically to another swath farther out, and transmit again for some portion of the synthetic aperture, and repeat that as often as needed to get the swath that you need. So this burst of pulses is shorter than the total synthetic aperture, and since you're only sampling a portion of that synthetic aperture, you lose resolution in creating an image from that shortened set of pulses. Yeah? Yeah, this is still like 1 degree. Yeah, it's very hard to draw this.
Okay.
I'm not the greatest artist, so.
And what is the other dimension?
This dimension?
Yeah, how is defined, that one?
So that's the range dimension, and that's defined by lambda over the elevation direction.
All right, yeah.
There's, of course, projection factors in here, because you typically, for these kinds of antennas, you have a planar array with phase elements arranged in elevation that allow you to tilt the phase without tilting the physical antenna. And then there's a cosine sort of theta factor that will affect some aspects of the swath. But to first order, it's lambda divided by the dimension of the antenna in elevation. That all make sense? So you get, because you're looking at only a portion of the synthetic aperture, you get coarser resolution, but you get a much wider swath. So there's another one that you obviously all need to know about, because Sentinel-1 uses this as its workhorse mode, and that's called TOPS mode, Terrain Observation by Progressive Scan. And in this case, it's a little bit like ScanSAR, in that you time share the synthetic aperture between various swaths. But in this case, instead of just continuously looking off to the side, you're actually sweeping the beam within that burst. Within that set of bursts here, you're sweeping the beam across in azimuth, so that you're sweeping more of the history. So you get more of the antenna shape of any given target. So you get a better radiometric performance. It adds a lot of complications to processing for interferometry, and whoever is talking about TOPS mode, probably Piyush, will talk a lot about this later. But it is the workhorse for Sentinel now, so you need to be familiar with its characteristics. You still have lower resolution in azimuth because you have a limited synthetic aperture, but you have the wider swath. And then there are other techniques. This is the one that we're planning to use for InSAR, actually, where you transmit over a narrower aperture in elevation and a wider aperture for receiving. And that allows you to get a wide beam on transmit and then effectively track the pulse electronically as you're going across the swath here. It defeats some limitations of the other systems where you can have multiple pulses within the beam on the ground without any ambiguity. I'm not going to talk much about this, but this is going to be used for InSAR 3 years from now. Okay, so I have about 20 minutes left. What radar can tell us? So we transmit a signal that has known characteristics. We're in control of this, unlike sunlight for optical images. So we know how much amplitude, how much power we radiate. We can set the polarization, either vertical or horizontal or circular. We control the timing and the phasing of the system precisely, so we should be able to know the phase. And of course, we select the frequency that we are going to use. So we can, if we're interested in a particular kind of target on the ground, whatever that target is, we can design our radar to exploit these things in the way that we see best fit. And that is related to the phenomenology of scattering, which is another, full-year course in electromagnetics. But with the very few simple concepts on scattering theory, we can sort of understand what radar is telling us, at least intuitively. And so if you look at a electromagnetic wave that's impingent on a sphere, and you solve the Maxwell's equations for what the scattering from that looks like, it's quite complicated. But if you look at basically the backscatter cross-section of the energy coming back from a sphere as a function of its diameter, you can see that for large spheres, ignoring all this sort of wiggling, for large spheres, the cross-section of a sphere is roughly its projected area. And if you have a very small sphere relative to the wavelength, then you get very little cross-section. So you can think of it, I kind of think of it as this little particle immersed in a sort of static electric field. If the wavelength's really long, it just doesn't see it. Whereas if the particle is large compared to the wavelength, there's resonance effects that are going on in the sphere, and you get a big backscatter. So the idea is small particles, not much backscatter. Larger particles, you get a lot of backscatter. So that's one concept that's relatively straightforward and can apply to other contexts as well. Another one is familiar to you from Snell's laws that I'm sure you all studied in physics at some point, where you have an electromagnetic wave that hits a plate, and some of the energy is bounced back, some of it bounces forward into the medium. If you look at it at an oblique angle, some of the energy scatters off at an angle equal to its incidence angle, and some of it is refracted inward, such as that. It turns out that the cross-section of a large faceted plate goes as the area squared. So these can be very, very bright if you are hitting an electromagnetic wave directly on. So with these two concepts, you can sort of build up some notion of what you see from a radar image. So if you think of the Earth as being made up of tilted facets of some finite duration, like our antenna length, then you will get a scattering off of that tilted facet. If it's like a mirror, most of the energy will go away, if not all of it. But since it's a finite antenna length, it has a beam width, just as we described, lambda over L, so you'll get some scattering in various directions. And depending on the tilt, you'll get more or less energy scattering back towards the radar. That's what you get for a smooth surface. If you add a little bit of roughness to that surface, then you'll get more scattering backwards towards the radar, and you'll get more scattering off in various directions. So you can build up a notion of surfaces from facets and these sort of random elements. And sometimes just thinking of the roughness of the surface in terms of a bunch of random points within a resolution cell, and then summing those up, depending on the size of those, you can use the concept on the previous page to calculate the cross-section. And the angle, the amount of energy you're going to get back is going to be related to this projection of that cell in the direction. So again, the tilt factor will impact how much energy you get back. So one question is, how rough is a rough surface? And one way to calculate that is the so-called Rayleigh roughness, and that is simply if you have a surface with two different heights right next to each other, and the wave comes in with some angle like that, then if the phase of this signal relative to that signal is roughly the same within a quarter wavelength or so, you'll say it's roughly the same surface. Or, sorry, rough is the wrong word there. It's approximately the same surface. So if that difference in height is less than a quarter of the wavelength, then you're good. So this is the formula for the Rayleigh roughness. If the height difference is less than lambda divided by 8 cosine theta I, whatever that angle is, then the surface can be considered smooth. And that's kind of similar to what you saw for the sphere. If you're sort of sized according to the particle size, it's considered a good scatter. If it's much smaller than the particle size, then you don't get much signal back. So in general, for a surface and volume scattering, if you're looking at an angle that's relatively pointing down, then surfaces are going to look kind of faceted, right? When you look down, you don't see a lot of the topo effects. You get a lot of bright facet-like scattering of incidence angles that are shallow. As you go further out in incidence angle, you start to approach this sort of randomly rough surface characteristic, and you start to fall off like the cosine of the incidence angle. And then when you get much further out, you end up with resonance phenomena called Bragg scattering, where the wave is coming in towards the surface, and if there's any kind of regularity in the surface, you'll get some resonance with that surface. So you tend to get a slight enhancement at the higher incidence angles than you would just by this random effect. So this is kind of what the backscatter of a surface would look like as a function of angle. So if you're designing your radar again and you want to understand the brightness characteristics of what you're seeing, this is sort of to first order what you might expect as a variability across the swath. So typically we look off to the side. I didn't really talk about that much, but everybody knows why radars look off, why these synthetic aperture radars look off to the side? Any ideas? The answer was originally military purpose. Well, there is an element of that, but that's not why we look off to the side. Yes? Yeah, exactly. So if, I'm not sure anybody heard the answer because you weren't quite speaking into it.
You will repeat, or I have to repeat?
I can do it, yeah. So the answer, which was correct, is that if you're looking straight down and the energy is going to both sides of the Earth below you, and you're sensitive to time or range, as we have been describing, you're going to get responses from both sides of the Earth at the same time coming back to you, and you won't be able to discriminate which side that you're looking at. So we have a finite beam width that we've been talking about, and so if we just tilt it off to the side, then we remove that ambiguity, the left-right ambiguity. Range is now proportional to time in an unambiguous way. So that's why we look off to the side, but the problem is that we get distortions relative to what we would like to see on the Earth. And here you can see a cartoon depiction of that, where we're looking off at this angle like this. We have topography on the ground with slopes up and down, and larger slopes and buildings and things like that. And this grayscale, shall we say, image is supposed to give you a notion of what we talked about on the previous slides, where if the slopes are tilted towards you, it tends to be a little bit brighter. When they're tilted away from you, it tends to be darker. If you're extremely tilted towards you, you get a very bright return, and if it's extremely tilted away, then you get shadow, you get nothing at all in return. And there can be cases where, for certain geometries, if the slopes are too high, then you can actually reverse the order in the image of where objects appear relative to where they should be. So this layover, shadow, foreshortening aspect does definitely complicate your interpretation of a radar image. It also adds to this variability in brightness. The topography adds the variability in brightness that may not be of interest to you studying the brightness of the surface. So the various surfaces will also introduce various backscatter characteristics. We talked about smooth surfaces versus rough surfaces. There'll be brightness variations relative to that. We talked about the layover and shadow up above. Forests are upside down. I'm not sure why that's upside down. Anyway, forests tend to be relatively uniform in terms of their backscatter because you're scattering from the volume, and urban areas kind of look like mountains. So when it comes to looking at a radar image, there's all kinds of factors in it that are related to the topography and what's actually on the ground. And the wavelength that you choose will determine, again, what you see, because something that's rough at one wavelength may not be rough at a different wavelength. So speaking of which, the longer wavelengths, again, they they propagate through or do not see objects that are small relative to that wavelength. So they tend to penetrate deeper into vegetation canopies or dry soils or ice surfaces because the scatterers tend to be smaller in general than the wavelength. The trunks and ground interactions, those tend to be not small, and so you do get a bright return there. For the shorter wavelengths, you tend to scatter from higher in a canopy or higher in a volume. And here's an example of an L-band image on the top and an X-band image on the bottom. So 24 centimeters and 3 centimeter wavelength. And so what's one sort of high-level thing you see in this image as a difference? Same spot, image at same time, the same system, but 2 different wavelengths. So to me, the one on the top has much more contrast than the one on the bottom. You can see areas here that are quite dark on the top and quite a bit brighter on the bottom all throughout. And to me, assuming these are properly calibrated and scaled, which I believe they are, what that usually is telling you is that the Earth looks rough at 3 centimeter scale in general everywhere. And that makes sense. Most things out in nature are rough at that scale. Even if you go out to a gravel, very flat-looking gravel surface, it's rough at the 3 centimeter scale. So you can see that if you're trying to discriminate different surface types, the so-called clutter, maybe that's X-band is not the best wavelength for that purpose. Maybe it is, depending on what you're looking at. So you can also control polarization, and polarization is one of those things that is, I'd say, in the last 10 years, really having a major renaissance. It was very popular in the 80s, then it came down for 15, 20 years, and now it's resurging again, especially in combination with interferometry. You can transmit, we can control our polarization as we transmit, so we can arrange the electric field vector vertically or horizontally, or some combination thereof. And surfaces which are oriented tend to orient the scattered signal that comes back. So by looking at a surface polarimetrically, you can say something about the orientation of scatterers. Here's an example from the Los Angeles area showing the city of Los Angeles with very different colors depending on where you are. And this has to do with the arrangements of the streets and buildings relative to the flight direction, the look direction of the radar. So here in, what is that, Santa Monica? The streets are arranged parallel to the coast, and the radar is flying this way, looking off to the side like that. So we're looking at a geometric scattering phenomenon from the ground to the building and back to the radar again, which is quite bright, quite strong. Elsewhere in the city, you can see the streets are oriented more at a 45-degree angle relative to that. So the scattering mechanism is different. So the polarimetric signature tells you something quite different. The one on the right here is a combination of polarimetric diversity and frequency diversity, so it's a little bit harder to interpret. It's just very beautiful, so I like to look at it. These are volcanoes in Rwanda and Uganda, and the sort of uniformly white areas are likely vegetated canopies, so you're getting a lot of volume scattering, you're not a lot of polarimetric discrimination, whereas these other surfaces are either open lava flows or other kinds of forests. So it's very, very interesting, rich data set, difficult to interpret with only 3 measurements and a very complex Earth, but still very valuable information. So I mentioned the radar equation before. Again, there's a whole segment on this in the other notebook, but I just wanted to mention it because you often hear about signal-to-noise ratio in looking at imagery, so I just wanted to introduce the concept there. So the radar equation is effectively a way of characterizing the signal-to-noise ratio of your system. You have a radar that's transmitting some amount of power. You have an antenna that has some degree of directivity. That antenna beam is a function of its size and the wavelength. So the more directivity you have, the higher the gain, as we call it. So more of the energy from that transmitter is focused in that one direction. It propagates a distance and falls off like a water wave that's a pebble dropping into the water. It falls off as 1 over r squared. And then it hits your target, which has some reflectivity or radar cross-section. So some of that power is then, the power density hitting that target is reflected back, propagates back to the radar another distance of r to the 4th, is received by the aperture area, and then there's some losses in the system, and then there's noise associated with the radar system itself. So the noise here is determined by the bandwidth of your receiver, and all these factors determine the signal-to-noise ratio. So if you have a very dark target, you don't get much signal back. If you don't have a good transmitter, you don't get much signal back. If you have a wide bandwidth, you tend to get more noise in your system. So you have to design all these things accordingly. And the farther away you are, the less signal you get back as well. All these factors are important in these SNR. However, oops, didn't mean to do that.
Just because you're moving in this direction?
So this is the sort of instantaneous.
Okay, so my question was just about if you had the SAR sensor and you were moving in instead of a horizontal direction, vertical direction, does that affect anything? Is that handled differently anyway?
In terms of the signal-to-noise ratio that you get? So that factor, this is sort of the instantaneous signal-to-noise ratio of a given signal that you transmit.
Okay.
So if you want to calculate that for some derived quantity based on a number of pulses acquired in some geometry, there's an integration factor that goes into this that is not represented here. So that will matter in terms of the ultimate SNR you get, but that's not represented in this particular equation.
Okay, thanks.
Yeah.
I was wondering if you'd comment on the temperature dependence, and what is the temperature of the Sentinel-1 antenna? Is this, 40 degrees Fahrenheit? I mean, it's sort of a little I don't have a good sense of why temperature comes in.
So temperature comes in because your electronics has electrons running around in it, and they have some mean velocity, which is based on their temperature. The temperature in space is quite cold, so you would think that it's not a big deal. If everything would be, all the electrons would just be sort of lazy and moving around. But you're looking at the Earth, and the Earth radiates like a black body. It's roughly 300 degrees Kelvin. So that is going into the aperture and heating up everything on the inside. So typically we say it's the noise temperature of a radar is around 300 degrees.
And that's the temperature of the target or the temperature of the antenna?
Antenna, the radar temperature, receiver temperature. Receiver temperature. Yeah. Temperature of a target doesn't matter.
And you're saying if I took a thermometer and stuck it on the Sentinel-1 antenna, it would be
Probably not, no. It's a antenna temperature, if you go and read the literature, is very complicated to describe. They're really effective temperatures relative to sort of the electron noise that you have in it. So it's hard to describe it in just one word what it means, but typically it's, did you want to say something?
Yeah, I completely agree. They don't
explicitly call it receiver temperature, but like for Sentinel-1 and others, you will see a field called thermal noise or noise. That sort of it's a catch-all for...
Yeah, it's a catch-all sort of average temperature describing how much noise there is in the system. There's amplifier noises that affect, there's the reflection properties of the receiver system. There's all kinds of things that go into that number. The losses also sometimes capture some of those things. It's not a trivial thing to figure out all of those things, but it's roughly okay just to say the temperature is around 300 degrees and you generally get the right KTB factor. Yeah.
With synthetic aperture radar, are we able to reduce the receive antenna area? Is that what you mean with this? Like with synthetic aperture radar, we are able to reduce the receive antenna area?
Reduce it for what purpose?
What I understand, like in space, we can't have big antennas because it is not feasible. So what we do, we somehow split the size of the antenna in that way.
Okay. So yeah, I understand your question, and the answer in that context is yes.
Mm-hmm.
Again, when I was describing the synthetic aperture, the beam width extent is like 18 kilometers for a typical antenna. Your synthetic aperture length is twice that. You would need a 36 kilometer long antenna to be able to get the 5-meter resolution we get using synthetic aperture radar techniques using a 10-meter antenna. So you're going from a 10-meter antenna, which is physically realizable, to a 36-kilometer antenna, which is not. And there's other issues with having a 36-kilometer antenna that's for the week-long course that we can talk about later. So.
Antennas flying in formation. Right. You
could put multiple antennas flying in formation. That's true.
Right. So then.
But it's
sort of like a VLA in space or something, right? You know, something like that.
That's true. You could do that. That also takes time and effort and money. So, yeah. Okay, I'm getting a little behind here, so let me just finish up. So SNR is one thing you can design for, and you could argue that I'm going to just crank up the power on my system if I don't have enough signal back from my target of interest. But that's not the only thing that you care about. The other thing you care about is the noise quality of the speckle. This is a coherent system, and remember we're worried about phase here. And so for each point on the ground, this electromagnetic wave comes in, it scatters off of all the elemental scatterers within that element. And so they will have, each one will have its own distance from itself to a reference surface, which they would all reference to, and they'll all have their own backscatter amplitude as well, because they're different things: trees, buildings, cars, people, whatever. So if you sum up all of those elemental scattering terms for this pixel, you're going to get some complex phasor. If you go to the next pixel over, which has a different arrangement of scatterers in it, you're going to get some other phasor. And that's going to be just an intrinsic property of this complex image. It's unavoidable. And even if you have more power on the ground, you're just going to get a brighter speckle pattern in your image. It doesn't help you in terms of discrimination of features on the ground. So this is a typical radar image, and probably you'll see this later when you do the first focusing example. Typical radar image, which looks very salt and peppery from pixel to pixel because of this speckle pattern. There's nothing you can do from a SNR perspective to change that. The only thing that you can do is do some sort of averaging to beat down that noise. So typically what's done is spatial averaging. There's some very fancy filters for spatial averaging that are done to reduce this. But if you take this and average it, it starts to look more like the mean background without all of that salt and pepper on it. But what does that tell you about your imaging system? Suppose you want to observe something with 10-meter resolution. You have to be very careful about what you mean by that 10-meter resolution, because most people think they can take their fully processed, full-resolution SAR image and get their results from that. But usually they have to do some sort of averaging in order to beat down this noise, in order to be able to create the product of interest. Similar issue is in interferometry, which we'll see in this afternoon. You have to do some amount of averaging to beat down the speckle-related noise in the interferometric measurement. So you end up with coarser resolution than you initially thought.